Hi, we're going to take a look at heat transfer, and this particular form of heat transfer we're going to look through is through solid materials. So if you have a material and you have a temperature difference at each end, so you've got temperature 1 over here and temperature 2 over here. Say for instance T1 is larger than T2. Energy will flow from the hot end into the cooler end through the material. Now the rate at which this energy moves, the heat over time, if you don't remember from chemistry, we express heat as a capital Q. The heat transfer rate is related to a few things. First of all, it's related to the material. So there's a constant that shows up. This K, the thermal conductivity, is the effectiveness of heat transfer through the material. It's very similar to the idea of conductivity in electricity flow. This property of the material is a constant for a given material. Other factors that affect the rate of transfer would be the area by which this passes through. So this area of the cross-section of the material, the larger it is, the more heat transfer you get. Also, what will affect this is the length of the material. So the further it has to go, the less the rate of heat transfer. Possibly the most important thing that affects this is the temperature difference from one end to the other, which we'll write as delta T. So the bigger the temperature difference, the faster heat will flow through the material. So this is the equation that we're going to be using in this video. Now, one thing to note, that the rate of heat transfer, the energy per time, is also power, which is expressed in joules per second or watts. So if you find yourself giving the power of the situation, just understand you could substitute that in for Q over T. All right, let's do an example. This is supposed to represent a steam pipe covered in insulation. The insulation has a thermal conductivity of 0.25 watts per meter degrees Celsius, and the thickness of this material, which I'm actually going to use a little d for that because all our t's are taken up, is 1.50 centimeters. Now, other things that we know about this is we know that the inside temperature is 200 degrees Celsius, and then the external temperature outside the pipe is 20 degrees Celsius. The question we're being asked is, what is the rate of thermal heat transfer if the length of this pipe is 50 meters and the circumference of the pipe is 800 centimeters? Now the formula we're going to use is the standard formula. The heat transfer rate depends on certain things. It depends on the thermal conductivity. It depends on the area through which the heat's going to flow. It depends on the length, in other words, the distance that it flows through, and that change in temperature. The only thing that's particularly challenging about this problem is that the area is not given, and there is some confusion here. The L in the equation is actually the thickness of the material. The heat will pass through the material on its way out. So you've got to be careful. That length of the pipe is not the L that goes in here, and you have to be able to make those mental shifts when you do problems like this. What I'm going to do next is let's calculate that area. I'm going to imagine that if I slit this material and unwrapped it from around the pipe, which is probably how it was installed in the first place, I'm going to get a somewhat flat sheet of material that's 50 meters long and has this dimension is actually the circumference. When you wrap it around the pipe, that becomes the circumference. 800 centimeters is 8 meters. So if I want to calculate the area of this, it's just going to be 50 meters times 8 meters, which is 400 square meters. Now I can actually plug the numbers in the formula and see what we get. So the rate of energy transfer is equal to the thermal conductivity, 0.25 watts per meter degrees Celsius, times this area of 400 meters squared over the length it passes through. Now, 1.50 centimeters is the same as 0.0150 meters. So I'll put that in here, 0.0150 meters. And the temperature difference is going to be 200 degrees Celsius minus 20 degrees Celsius. Before we plug the numbers in the calculator, let's double check and make sure our units work out. Here I've got meters squared over meters, which will give us meters. This is going to be in degrees Celsius, the temperature change. And finally, you've got this watts per meters times degrees Celsius. So if you can see, the m's are going to cancel. The degrees Celsius are going to cancel, and we're left with watts, which I remind you, I already said that energy per time, or joules per second, is also the same thing as watts. So this works out. Let's go ahead and put the numbers in the calculator and see what we get. Okay, the number I come up with for the rate of energy transfer is 1.2 times 10 to the 6 watts. It's pretty massive, but again, this is a steam pipe surrounded by air. You're going to lose a lot of heat that way. Now, if you take the insulation away, you would lose a heck of a lot more. So that's why we have to insulate something like this. Anyways, this is the type of problem you're going to be doing on your worksheet, and hopefully you will figure this out and have good luck with this.